So in, it was probably around the turn of the century, 1900s-ish, J.J. Thomson discovered a smaller particle than the atom. So Dalton said that the atoms were indestructible, and now Thomson is finding that the atoms themselves have parts. So the electron is a negatively charged particle. It's much smaller and lighter than the atoms, are, and electrons are uniformly present in many different kinds of substances. So it wasn't just one particular kind of atom that you could chip electrons off of. You can get electrons out of any kind of atom. All atoms contain electrons. So this was a big deal. So he discovers electrons, and then we have to have some ideas about, well, what are the electrons doing inside the atom? Is there anything else in there? What's going on inside the atom? So Thomson proposed that the electrons were held in a sphere of positive charge that would balance the negative charge of the electrons. Because they knew that atoms didn't have a positive or negative charge. They were neutral. So if there's negative particles in there, there must be something positive in there as well. And so Thomson's model has come to be known as the plum pudding model. Have any of you had plum pudding? I have not. I've read a lot of British authors, though. Plum pudding is an English dessert. It doesn't sound all that good, but let's Americanize it. Blueberry muffin. Blueberry muffins, anybody? Okay. If you haven't had one, you've probably seen one. So you've got this, white vanilla-ish muffin cakey part, right? And it's got blueberries in it. They're just kind of scattered around. This was his idea for what the atom was like. That this positive charge was like the muffin, and the blueberries were the electrons, just kind of dispersed through it. You got to start somewhere, right? So this is a picture of that. I don't know why it's pink. Okay, so Rutherford had actually been working for Thomson. I believe he was one of his students. So Rutherford was trying to test this theory of this model of the plum pudding model of the atom. So he's trying to show that this is correct. So he's going to do some experiments and see what happens. So what he did is he took some tiny positively charged particles, they're called alpha particles, and he bombarded a very thin piece of gold foil with these alpha particles. And then he had this screen around here that would detect the particles so you could see what happened to them. And what they found was that most of the particles went straight through the foil. Some were deflected a little bit, and some were deflected at sharp angles. So what does this mean? Well, if the plum pudding model were correct, what they expected was that these alpha particles would blast straight through. They're not going to hit the blueberries, they're just going to go straight through the cake. And most of them did. But the actual result was that some of them came back. And Rutherford said, this is a quote, that this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Can you imagine firing a 15-inch shell at a piece of tissue paper? It's going to go straight through, right? That's what they expected. All of these particles just go straight through. But it comes back and hits you. You'd be surprised, wouldn't you? They were shocked by this. What on earth is going on that these particles are bouncing back? Obviously, the plum pudding model is not going to work. So they come up with a new model. Well, based on our new evidence here, what's going on? So this led to the nuclear theory of the atom. The nuclear theory says most of the atom's mass and all of its positive charge are in a small core called the nucleus. Little tiny part in the middle, that's where all the positive charge is and most of the mass. Most of the volume of the atom is empty space. And in that empty space, we have the negative electrons, little teeny tiny electrons, doing something. And the number of negatively charged electrons, which are flying around outside the nucleus, is equal to the number of positively charged particles, they're called protons, that are inside the nucleus. So the atom is electrically neutral. Let's look at a picture of this. So here's an illustration. This is not to scale. Here's the nucleus. Inside the nucleus are the protons, and we'll talk about more of those in the next section. There's also neutrons in there. This is where almost all the mass of the atom is. And then out here are some little tiny electrons doing something. That dense nucleus makes up more than 99.9% of the mass of the atom. The electrons are occupying most of the space but have almost no mass. So really, atoms are mostly empty space. And yet, if you knock on your chair, it doesn't seem like it's empty space. It seems pretty hard, right? You fall down, you hit your head on the cement. It seems pretty solid. One way to think about this is imagine water droplets in a cloud. So, big cloud, right? What's it composed of? Little tiny water droplets. Do the water droplets themselves occupy much volume? No. The volume of the individual water droplets and their mass is very, very small. And yet they're distributed in this big area, and so we see this cloud. It looks solid, but it isn't, is it? You can just pass your hand right through it. But that's what the electrons are like, these little tiny particles, but they're occupying a big space because they're moving around and there's a lot of emptiness in between them.